All right. Okay. So yeah, thanks for coming to my talk. This is my first Pi Ohio talk, actually second time attending, so pretty excited to be here. I'm excited that I could wear the shirt somewhere and have people get it, and not instead of look at, like I'm making some kind of political statement or something. So I'm excited for that too. A little bit about me. I've been in the software biz for a long time now, mainly doing C, C++, mainly doing C, C++ development, but a lot of incidental Python. So I'm definitely not a Pythonista by any stretch. So any misstatements I make are out of ignorance, not malice. But so this thing that I'm going to talk about today, Google protobuf, is something that I've used it's just popped up time and time again as a good tool to fix problems that I've encountered. So let's get on with it. What are protobuffers? They're designed by or developed by Google. It was developed as one of their, what they call them, I don't know, 10% projects. They're extracurricular projects. So, but it's been widespread adopted throughout Google. They use it in, I don't want to say all of their projects, but many of them. It's an extensible language, platform neutral, efficient way to encode data. So, yeah. Okay. So, at its core, what it does is it takes various arbitrary data, makes it as small as possible, not using compression, but just using clever encoding. And as I said, it's widely used in Google. I think I read on their web in the GitHub page that somebody did a search of their repo, and there's over 40,000 .proto files, which are kind of the source code of that. So it's open source and patent free. So that's all good. The three benefits that you get from protobuf that gets me coming back to it time and time again is the backward compatibility is easy to get. They designed it for that purpose, so they don't have to upgrade all their servers at the same time to talk the same language. The encoding is very efficient, and the code to parse these buffers is automatically generated. So there's not a byte of handwritten code where you have to, this is this kind of field. I need to convert that to an int or whatever. It's all built in. This was largely stolen from their protobuf GitHub as well. Basically, they made a comparison to XML. The XML is great for a lot of things. I use it a lot. It's very, very readable. It's very wordy, though. If you're doing something at scale, so either something at the scale of Google, where you have, I don't know how many, tens of thousands, hundreds of thousands, however many servers they have, they need something that scales. And when I don't want to see what their bandwidth bill is, but shaving 1 byte off of every packet they send to their server, I'm sure saves them, a lot of money. So compared to XML, it's 3 to 10 times smaller, 20 to 100 times faster for parsing. The data accessors are automatically generated, so there's a simplicity there that you may not get with XML, at least not that I'm aware of. It's really in addition, so what attracted me to it for this talk is that it's, in addition to using it at large scale deployments all over the world, you can also use it for very limited bandwidth or limited RAM, limited storage, so forth. So like little devices. So that's what I'm going to show later. I've got some kind of antiquated little devices, but that's what I had, so that's what I went with. Did anybody go to Greg Svoboda's talk yesterday? No? Yeah. Okay. He showed off this little $5 system on a chip, the ESP 8622, or 8266, yeah. And it was, he threw an Arduino into the audience that here, you can have this. You don't need to use these anymore because that thing is pretty awesome. So I don't have those, so I have something maybe hopefully a little more familiar to people who aren't into like small computing devices. So, and I should add that all this, everything, the slides and my code and everything will be, it's on GitHub. So at the end there'll be a links page, and so you can pull all this stuff down and look at my terrible code. So that's kind of the reasons to use protobuf. Some of the reasons that you might not use it is if you have really big data sets. The Google protobuf page says if you're sending like more than a megabyte in a chunk, maybe think of something else. That said, I read in a forum recently that somebody was complaining about, we're not so happy with protobufs because we're throwing around 64 megabyte packets and it's just not holding up. It's like, well, it wasn't designed for that. And as you asked, it's a binary format. They're not interested in making this human readable or editable. This is something that you put in the pipe, it shrinks it down, sends it over the pipe, or maybe you're saving data, to a hard disk or whatever. But the idea is it's not meant to be something you can just open up a browser and say, oh, well, let's look at all the fields in this structure. That's not going to happen. So, and because of that, you can't do things like interleave other, like like XML, it's really easy to stuff some JavaScript or HTML or something like that in there, but this, you're not going to do that. Okay, so stop me if you've heard this one, being Python developers, but they've kind of had a schism in their world too between Proto 2 and Proto 3. It's not fair to say it's a schism. Proto 2 came out 10 years ago. A lot of people use it. Last year, July 2016, they released stable Proto 3. It's recommended for all new code.
Just say backwards compatibility was one of the benefits?
It is. But in terms of making your message definitions and stuff, because the part of Proto 3 is they really made the language less wordy and just it's better to use it this way. It's basically an iteration on Proto 2, and yeah, they kept backwards compatibility as much as possible. But generally speaking, you wouldn't be mixing the two anyway. It's more, the backward compatibility is more within when you set up, initially you set up your system and you have your packets and whatever that you want to send, and then later as the system grows and evolves, you're like, oh, we got to send new data, we don't need that data anymore, and so forth. That's the backwards compatibility that I'm talking more about. But the only reason I really mentioned Proto 2 is because a lot of the docs on the GitHub for protobuf, all their examples are still in Proto 2. So it's going to, just to avoid, prepare you for the possibility of confusion, there's going to be, you'll look at the examples, you'll look at the language reference, and they don't match up. Well, I shouldn't say that. All the examples will be in Proto 2, but you want to do it in Proto 3, and it's not hard to map one to the other. Okay, so how do you use it just from a workflow standpoint? So the protobuf messages are defined in a plain text file, usually with .proto as the file name extension, and those are then compiled down to the generated your target language that you want to use with protobuf with. Use this proto compiler to generate the data access classes in the target language that you're interested in. So Python 2 and 3, Java, C++, there's all the, and there's also a lot of additional third-party plugins. So these are the ones that they support just kind of out of the box. You can get additional third-party, open source plugins that people have written to support other languages, So it's definitely a vibrant community. A lot of activity on this project's GitHub is, even now, even after 10 years. So it's definitely a thriving and broadly used technology. And you can get pre-built binaries, so you don't have to deal with any of the problems of, sometimes you've got to build the packages from source and all that. You can do that if you want, but especially with Python, they've had the Python package index. I'm pretty sure, I know they have it for Python 3, probably have it for Python 2 as well. Just, you can just do a pip install protobuf, and you're done. So the basic flow goes like this. You start with your proto file. You run it through the proto compiler. In this case, for our purposes, it generates this foo_pb2.py. This naming isn't so flexible. They always append _pb2, even if you're in proto 3, which is kind of yeah. There's some rough edges that I don't know why they haven't sanded them down, but just be aware of that, because it's in the .proto file that you specify which version of the language you're using, and it generates the right thing, but it doesn't reflect in the name. And then you just import it into your application, just like you would any other Python module. Okay. So, as you might expect, any kind of data encryption language is going to have support for a lot of numeric types, so double float. They got a bunch of different 32 and 64-bit integer types, which I'll talk about a little bit more later, because there are important distinctions about those. String support, most languages UTF-8 only. Python, there's some kind of Unicode support that I haven't fully grokked, but if that's important to you, it's definitely an option. Bool, we all know what that is. Bytes, though, if their string type doesn't cut it for you, or you need some other bag of bytes, bytes is the type for you. Enums, if you're familiar with C and C++, they have the concept of an enum. It's basically just a bunch of named constants that are in a group. So those allow you to have kind of a set of predefined values that you can give meaningful names to, instead of, oh, that's type 1. You could say, oh, that's a Corvette. And then finally, there's this any type, which is, it's like a bag of bytes, but you can also give it a URL to say, this is how you interpret what this bag of bytes is. So I haven't used that before. It sounds pretty cool, but just haven't used it, so I couldn't say too much about that. Okay. So yeah, I mentioned before that there's different ints for different uses. Most of them have a variable length encoding, and that's where protobuf picks up a lot of its compression, or I don't want to call it compression, encoding efficiency. But some of them don't. So it's important to know that the type of int that you're using matches what the values you expect to go into it. So, for instance, if they have an int 32, which sounds like, oh, you can put any kind of integer in there. Well, no. If you're expecting data that's mostly positive integers, then int 32 is okay to use, because if there's a possibility it might go negative, then int 32 is probably okay. But if it's often that you're going to have signed values that go negative, then you would use the sint 32. And similarly, if you know they're always going to be positive, then you would use the uint 32. And the reason being that they've got, well, I'll get into that in a bit. I talk more about the encoding. And then finally, doubles and floats they don't encode very well, because, generally speaking, there's, if you take the value of 1/3 and put that in a float, you probably don't care about the 19th digit of precision, but the protobuf has no way of knowing that. So, if at all possible, scale your floats and doubles into int values that you can get a more compact range from, and you'll get better encoding. Okay, some other notable features. messages can be nested, so you can have, it's kind of like, you can think of it as C++ classes or the equivalent in Python of basically you can define a class within another class such that only you have some scoping effectively, so you can allow a little bit of a OO, I guess. I mean, this isn't meant to be like a full programming language, but it does have kind of an object-oriented way of specifying how your data is structured. Likewise, you can use messages as fields within. So really, if you know C or C++, this is, you're going to see, I'm going to show a simple proto in a minute, and you'll see that it's basically looks like a C struct. And that's a good way to think of it if you're familiar with those. It also, the language has associative maps, so you can, it's like a dict in Python. They've also, in Proto 3, added in addition to the binary encoding, you can do a JSON encoding and decoding, so give you a little more flexibility with maybe existing deployments and such. And then you can also import definitions from other protos. So it's, again, using the C metaphor, it's just like a header file that you can bring in to build up more complicated messages, because you don't generally want to try and stuff all of your message types into one proto if you don't need to. Okay. So here's a simple proto file. As you can see, it's like I said, it looks a lot like a C struct if you're familiar with that. There's some keywords like, so message is a keyword. So there's data types that I talked about before. There's enum keyword, and that's a pretty good example of what a very simple protobuf message might look like. So I've named my message type sensor data. So it's got a temperature, a humidity, and an enum that I use so I can say which kind of units I've specified the temperature in. And so now, here's where it diverges a bit from C. They have these tag identifiers, and this is kind of key to how they achieve their encoding efficiency, because these tags specify basically the order in which messages are kind of serialized, deserialized, and also they're used to handle cases where, because all of these, I guess I should mention that all of these fields are optional. So I could send an empty, well, not an empty sensor data, but I could send a packet that's got a sensor data message in it that I didn't change anything in, and protobuf will just supply default values to all those things. And in that case, it will send it very efficiently because these are all considered optional. The sender, when they encode this message, it actually shouldn't encode to very many bytes at all, because it's not going to send any of the values that I didn't set. It's just going to basically send a token saying this value should take its default.
You have to specify the tag IDs, or do they default to say the order in which they're declared if you don't specify?
Right, so the question is, yeah, do you have to specify the tag IDs? Yes. That's kind of an irritation, but it actually turns out I used to think, well, why can't they just do that automatically for me? But in a minute, I'll get to like some of the reasons why they can't. But yeah, you have to specify them. Okay, so this is again, I mentioned we use the Proto-C or Protoc compiler is what generates this code that does this parsing and encoding of the data that's specified in the proto files. That command line there is what you would typically use to generate a Python output. You can generate all the languages that supports. You can generate them all in the same invocation of Protoc. So if you've got this cross-language system that you're developing, and you want to generate Ruby and Java and Python and all that, you can specify them all in the same command line and have it all generated at once. And like any good utility, you can invoke it with help, and it will help. And then the output is in the case of Python, it's going to be a static descriptor of each message type, which, along with a meta class, you can use in your Python program to access the class at runtime. So here's an example of what serializing that previous message would look like. You create an instance of one of these sensor data objects, and so the name comes, the module name comes from the file name that Protoc generated. So simple in this case, PB2. And then you set your fields to whatever you want them to be. And like I said before, if you leave one out, it'll just get the default value. And so I didn't have to set all these, and I probably to demonstrate that, I probably shouldn't have set them all. But anyway, and then you call serialize to string, and that does just what you think it would, which is takes that sensor data message, turns it into a little string of bytes, and then you're ready to do whatever you want to do with it. Send it over the wire, whatever. On the other end, the receiver of this data, they get this serialized data chunk. Again, they create a simple sensor data object called parse from string, and then they can access the fields to do whatever they want. So, and again, if the sender hadn't sent, say, a temperature, when I read this temperature here, I would just get the default value, which is typically for numeric values, it's 0. And in fact, if you look back at this, one reason, see there's this enum here, it's got a value of 0. You have to start your enums with a value 0, because that's what Protoc will understand to be the default for that enum type. You don't have to have them in order after that, but you do have to have a 0. All right, so, okay, let's do a little command line thing here. I'm just going to show where, simple example, where do I want? No. Okay. It's not showing. Hello. Now I did it. It just stopped. I don't know why that isn't displaying, no? What's that? The projector's on. I can see the light in there. Well, I don't. Well, this is an unexpected bonus. Let's see if I can figure it out here. I want to. What's that? Yeah. Yeah, but this is never happened. This always works. Yes. There we go. This did it. All right. Sorry about that. Okay, so I'm going to just show you a little example of that. So here I've got that simple proto again. So this is what I showed before. In addition, I'll just point out here that there's that up at the top here. I specify the syntax as proto 3. If it's not there, it assumes proto 2. So again, this is just what we were looking at before. And now that example that I showed, well, first of all, I'll show you how to do that. So Protalk. Oh, pipe. Okay, I can type Python out. Dot. Proto. Okay, so that's how you're on the compiler. Pretty neat, huh? And then we'll run the simple thing. So let me just scroll that up a bit here so everyone can see. So so you can see the payload length is 9 bytes. So it's sending basically 12 bytes of data because there was a float, an SN32 or a U32, and an enum. So mapping that again to like a C world, that would be, if you were just sending a raw struct over the wire in C, you might naively just dump the struct, and that would cost you 12 bytes. This is only 9, and it's also got the structure encoded in it, so you can see already it's a reasonably, decent encoding savings over just putting a raw bytes on the wire without even getting the structure that you need. So I'm probably saying this poorly, but this is less bytes to send just the raw amount of data that you would otherwise, but you're also getting the structure of the data in that encoding as well. So is that clear? Make sense?
Yeah.
Okay. Good. My job is done. Okay, so yeah, let's go back to this. Hopefully it doesn't mess up the display. It will put me at. You can see I'm an expert at giving presentations. It's very smooth. Yeah, so there we go. Command line. All right. So let's talk a little bit about backward compatibility. So Proto 2 to Proto 3 is not what I'm talking about here. This is more along the lines of you've got a server or a device deployed in the field, and it's using like the early version of your protocol definition. And let's say now you want to add some fields or change how it's set, the structure of it or whatever. Protobuf's got that built in, and they just have a few rules to guarantee backward compatibility, and that is, one of them is that those numeric tags that I mentioned earlier, you can't reuse those once you've deployed it. Like, let's say I want to get rid of the temperature field, so that was tag 2. Once I've deployed that, I can't reuse that even if I want to stop using the temperature field. That's just part of that allows the old deployed devices to keep functioning when they get a new message that doesn't have that field. So new fields are ignored by old clients, and likewise, if an old client sends a field that's been deleted, new clients or new users of the protocol will just ignore it as well. So that's kind of the beauty of it is you don't have to care there's none of this. I mean, you can still do it, but you don't have to do an explicit check when you get a packet. Oh, is this a version 9 of the packet? Then do this and this. Instead, you just say, oh, I'm going to read this packet, and if temperature's there, great. If not, deal with that. But if you know up front that you have to deal with the possibility of getting default or missing data, then versioning, becomes not such an explicit problem. You just deal with it implicitly when you're deciding how to handle your packets from the start. Okay, so and then the encoding efficiency. In that previous example, I showed there was 9 bytes to send 12, plus the structure was in there too. The way they do that is by looking at the properties of the data. And for instance, like when you're sending integers, a lot of the times the integers you're sending are not 2 to the 23. They're 12. Yeah. So the guys at Google, figured, that's the common use case. So they use a couple of approaches. One is called var ints, which is basically if you only need, say, a byte to encode a value, then just use a byte. And they do that by basically using the most significant bit of each byte to signify specify whether or not the value continues. So, and zigzag encoding, so that's for when you have a situation where your values, excuse me, can jump around 0, so negative and positive. Zigzag encoding is another way, and you can read the details on the GitHub about how it works, but basically the idea is you keep all those small magnitude numbers should have small encoding. And as I mentioned before, the selection of the data type makes a big difference in the how efficient the encoding is. So if you use an int 32 or 64 for negative values, protobuf is going to encode those using 10 bytes each for the 64 value, the int 64 case, and maybe even the int 32 case. So definitely you need to make some, intelligent decisions about your type of data, your representation of your data. And then also the fields that you use, that you expect to appear frequently, those should have lower tag numbers than those that don't. So like the first 15 tags are going to be your most frequent tag fields. Those will get encoded using 1 byte for the tag information. And then the next step up is to 2047. So your first 20,000 or 2047 field values should be your most common ones. And then beyond that, it doesn't matter much. Okay, let's do another command line thing. See if I can lose the display again this time. Correct. Yeah. They don't have to be sequential. They just have those few restrictions about. I think you have to have one that's got tag 1, and then, but after that you can go nuts with ordering. Yeah. Okay, so just another example showing the efficiency again. So let's see here. Let's cat. This one's a little more. It's not going to be. I'll just cat this here. It's a bunch of different ways of encoding that same message. What it boils down to is I've got a proto here where I want to just show how the choice of data type can affect the encoding efficiency. So what I've done is I've taken that same sensor data guy again, and I've introduced this new sensor data history message type. So basically, I could send a bunch of sensor data messages all in one group, and in this case, I've written a little Python script to just bundle up a package of 20 of them, and just to show the how the efficiency can vary based on the encoding that you choose for the values. So, in every case, it's sending 20 of those sensor data messages, and again, in a C++ world, that would be the equivalent of 12 bytes of data. So you've got your temperature is 4 bytes, the humidity is 4 bytes, and then the 4 bytes for the unit type. So in the first case, I used a float to encode them, and also I varied the kind of range of values just to show you how the encoding can vary based on the values that you're putting in those fields. So here in this case, I've got some negative. All my numbers are negative, and so you can see sending this float is still 220 bytes for 20 of those sensor data. So it's 11 bytes per packet or per struct, which is still less than the total size unencoded or uncompressed, and it's got the structure in there as well. But then you see if I use sint32 instead of a float, now I'm down to 9 bytes per sensor data message, but now if I go down to now all my values are positive. So now you can see the difference between using an int. So up here, I was using an int 32, and I was putting all negative values in there. So I was ending up with 17 bytes per message. Now, using the right data type, I'm down to 180 bytes, so 9 bytes per sensor data message. So the point is, data type matters. And then when you get down to really big numbers, you don't see a lot of savings. Yes.
So you said that one is better for negative and two better for positive. They're identical when in your example, when they're both, is it that when you get into larger quantities of the data that?
Okay. Yeah. So the question is, what's the difference between sint and int? Is that?
Well, more the point is you stated they were different, and on your second example, they have the same amount of data.
I was saying the int 32 versus this int 32.
I gotcha.
Yeah. So, yeah. Sorry. Thanks for clarifying. Yeah. So, yeah. Up here, all my values that I'm putting into my temperature are negative, and I'm putting them into an int 32. So that results in this really inefficient encoding. But down here, my values are all positive because they're right around 50, and so the using int 32 doesn't penalize you there because none of the values have gone negative. Any other questions on that? All right, moving on. All right. Okay. Back, yeah. All right. So, not yet. No questions yet. So, now I wanted to give a more in-depth worked example of how this all kind of rolls together. So I've got over here, I've got a Raspberry Pi and an Arduino Mega, although I got it working on a Uno as well. The point being, this protobuf is running on both of these, and this is a Mega, so it's got 32 megs of 32K of storage. This protobuf plus the whole Ethernet stack takes about 10% of the storage on that Arduino. And then on the Raspberry Pi, it's we're not so concerned about storage and such.
How big is the protobuf executables?
Well, it depends on the language. So like,
Say for C, for a little tiny bit.
so for C in particular, there's a third-party package called NanoPB, and that's what I'm running on the Arduino. That's I think they said 3K is the the size of the library on the embedded device. So so that Arduino is running C, C++. It's the Arduino language, which we all know is C, and that's what's running on there. So all right, yeah. So what I've done here is I've got basically an extension of that sensor data class. So let's say I've got I've come up with a simple. I've got my little network of Arduinos deployed all over my farm to give me temperature and humidity readings throughout the day. And let me just show you what that looks like. How's my time doing? 2:08. Okay. Where is controller? No. Oops. Okay. So here's, I won't go into all the particulars, but basically this is the message system that I've set up. Basically, I've set up this is kind of like the top level message that is used to communicate between my deployed Arduinos and my controller guy that's sitting on my laptop or my desktop or whatever at home. And this is like just a simple protocol that I've set up so that I can, when the devices in the field want to connect to the controller, they send one of these connect messages. When the controller wants to tell it to do something, the controller can send them a command message. And right now, the only command type I have is report. So that's what that third report is. That would be like the deployed nodes would be using report messages to report their data back to the controller. And here's the report. Should look familiar, at least for the temperature and humidity part of it. There's our friend sensor data. So basically, here's an example of nesting. So I've got my report, and within the report, I've nested the sensor data class or message type. And then down here is an actual instance of the sensor data field. So this report message has two fields. There's a device identification field, which is defined up here, which is an ID and an AIM string. And then that's used for a lot of so for like connect message, basically I can connect to the controller, and that allows me to identify who I am so the controller can keep track of who's who. So that's, okay, that's all well and good. But so now I've written a little controller class that basically sits there and waiting in a thread for network connections. Now, because I'm a coward, I didn't do this with like wireless devices, so it's all hardwired Ethernet. But don't let that distract you, because it works just as well, in fact, even better over low bandwidth connections. But this is just so I had one less potential disaster for this talk. I get Greg Svoboda, who he did all his wireless, and it was like real-time debugging, and yeah, I don't have the heart for that. So, so I just did it all wired. But don't hate me for that. Okay, so anyway, I got my controller is running here on my laptop, and it's waiting for UDP connections from anything that speaks, that knows it's there. So let's see. So I'm going to go ahead and, so I've got, this Arduino is just set up. It just, the first thing it does is when it powers up is it just tries to make a connection. So I'm going to just reset it now. And now in a few seconds, we should see, a response coming to the controller that says, yeah, all right, I got a connection from, that IP address. And so now the controller is going to periodically send messages to the Arduino saying, every second, or I think it's every 5 seconds, give me a report of your current data. So you can see it's reporting temperature and humidity. Another cowardly thing, that I didn't have temperature sensors or anything like that. These are just random numbers. They're randoms, but they have variation, so it looks like it's realistic, but it's not. It's really not 27. Well, it might be 26 degrees Celsius. What's that? Okay, so yeah, that's neat. So now we got this guy running, and let's say now it comes along, and I've got my Raspberry Pi here, and I decide, you know what, that thing's got a lot of power. I can send a lot more information, so I'll send a little bit more, and that is. And that's what this is. So this is fancy sensor. So if you go to my GitHub repo, you'll see all the code laid out. And I think I called the Arduino one is called Puny sensor, and this is fancy sensor. And fancy sensor does so much more than puny sensor. So that's, do I have the proto file here? Did I cheat? No. It's called sensor version 2. So now, is that readable? Yeah, okay. I've added a few things to this protocol. So now I've added this history. So I kind of denoted my changes for version 2 of the protocol with this comment here. Protobuf doesn't care about comments, so I've just put it there for illustration purposes. So inside of my device identification message, I've also added this new field, keeps history, so that the controller can act accordingly. Also, I've also added our new commands. So in addition to reporting data, now I can also tell the remote guy to report data history and clear your data history. So, and and then there's some adjustments here to the sensor, so the report message is kind of scrolled off there, but the important thing is now I've added this repeated sensor data history field, which this repeated keyword tells protobuf you can have 0 or more of these, whereas normally, like in the field right above it, data, you can only have 0 or 1. This repeated says 0 or more. And then the top level message thing's still the same. So like right now, if I run my fancy sensor, and yeah, so I'll pop over to this window. So you see it's recognized this new connection right there. So there's device ID neat, and the device name is El Luchador. But you can see it's still only sending old data. So for here from 1337, or not old data, but it's only, the controller doesn't know that this is a fancy sensor yet, so because I haven't upgraded the controller yet to speak the new version of the protocol. So the new fancy sensor is already sending, or potentially sending, this new version of the protocol, but the controller isn't asking for it yet. So now, let's go ahead and kill that controller, and let's run controller version 2. So now let me reset this to get the old Arduino, continuing to send out its old boring data. But now, okay, look at this. I just connected my Arduino connected, so it's still using the old protocol, but it's the controller is reporting, oh hey, look, it doesn't keep history. So now I know when I talk to the Arduino, I know not to send it things that are germane to keeping the history, like these new commands, like send me your history and clear your history. It could send it, it's just going to get ignored. So it's not like you have to carefully check for this. It's just more for keeping things sane on the controller side. But so now, if I go to my fancy sensor and I run version 2, now I should mention here that, so that fancy sensor was actually running the old protocol as well, but now it's running the new protocol. So I guess I lied there before, but now I should see here. So now it's you can see the old Arduino is still using the old protocol, so the controller is telling it just send me your one data chunk. But now the Raspberry Pi is using the new protocol, which keeps history, and so now it's on the Raspberry Pi end of things, it's every 5 seconds it's taking a new data reading. So it's taking temperature, humidity, rainfall, so cumulative rainfall, and barometric pressure. So what's going to happen here is you'll see it start to building up, and then once the controller gets to a certain number of iterations through this loop, it's going to send a clear your data history message, and so you'll see all those values go away, and it'll get reset to. So okay, yeah, so there it happened there. So did a report, and it's already catching up again. But so here's where it had, in the time that it sent the last report and they got the clear data report, the Raspberry Pi had already taken 2 readings. So that's why there's 2 there. But really, trust me, it works. Okay. So, excuse me. Yeah, so that's what? 219, all right. Okay. So that's what I got. Any questions? Oh, yeah. I guess I ran right up to it. Sorry. But we have a break after this, so if there's a lot of questions, go ahead.
Off the top of your head, are you familiar with the binary encoding used under the
Well, a little bit. So it basically it breaks down to there's an initial byte, and that's got like the specifier of what the first field that's in this message is, and then if that message is there, then that message's data, or that field's data is there, and then it has the next bytes or bits really that tell it, okay, is field 2 there? Okay, if field 2 is there, then here's field 2's data, and so forth. So, but that's kind of vague.
It's a lot like ASM1, maybe, under the hood. Do you remember ASM1?
No. Okay. I don't even know what that means. But you back there?
So your info with or for the network with UDP fairly straightforward. You've got one message decoded. If you're accepting messages over TCP, is there a way to know when you're asking the message, or read message and write over your messages?
Well, so the question is, how do you know when you've hit the end of your message, right? Yeah. Yeah, so this doesn't solve that problem. It's so like for my examples, what I did was I took that encoded payload and I send an extra byte as the first byte of the packet. It's the size of the encoded payload. So I know, so if it's a TCP packet, it gets busted up or whatever. If I read, oh, there's supposed to be 19 bytes and I only got 4, I'll wait to get the rest of them. Yep.
Is it Indian aware? So if you're writing on different systems, sending messages, it's aware that it was encoded on a little Indian system?
Yeah, it's not going to matter. It'll yeah, it takes care of all the network and coding. Yeah. Just to repeat the question, does endianness matter? No, it doesn't. Sorry.
I was going to ask, is there any way to back out what the protocol was? You can only inspect the messages. I've seen some like Android games that use protobufs.
Oh, so you want to reverse engineer I think there's enough information on the protobuf GitHub that describes the encoding that you could figure it out. It might be a little tricky though with like fields that are omitted, so because everything's optional. So if they only send the check for valid license key, message every 20 minutes, you may not catch that, and you might not get the full protocol. But yeah, sure, I think you could do that. Yeah, so you're saying there's Wireshark modules for that. I think you have to have the proto file of that, though. I may be wrong, but I think that's what I remember seeing about that. But anyway, it should be possible. You can, give it enough time and enthusiasm. Yeah.
You control the defaults in the protocol.
So the question is, can you control the defaults? Not in Proto 3. So that's one of the changes I made from Proto 2 to Proto 3. Proto 2, you could specify an arbitrary default, which was a nice feature, but it made language generation a lot harder, at least for some languages. So now they have these rules like, if it's most numeric types, the default is 0. The enum default is the tag 0 default, is the default, and like that. So in my mind, that was kind of a sad thing to lose for, between going from Proto 2 to Proto 3, because I use Proto 2 a lot in past stuff, but yeah, you get what you get.
And one more question. What's your sense of the trade-off of efficiency? You're packing things onto wire type, but it takes a lot of code or execution time to pack it that tight. How bad is
well, just going on the protobuf GitHub, their comparison to like the equivalent XML parsing was that it was 10 times faster. So it's because it is so less wordy, you just have that many few bytes to chew through. And it's not doing any kind of fancy compression, it's not, applying some kind of convoluted algorithm. It's a pretty simple algorithm, so it's pretty fast.
If you're on a tiny micro, the competitive technology wouldn't be XML, though. It would be a custom formatted
Right.
binary protocol.
Thank you for mentioning that, because
People only got,
Yes.
something
And
change the whole
so
library.
the benefit over that is you don't have to now keep, yeah, you have automatic parsing and you don't have to worry about, oh crap, we changed byte 3 to, now it's 2 nibbles. And, you don't have to do that. It's all taken care of for you. And
You can only do that if it would only be an advantage to do it the other way if you run a really tiny micro.
yeah, if you're an electrical engineer, yeah. I'm an electrical engineer, so it's okay. Somebody was raising their hand back there? Yes, no? Okay. Well, I'm going to be here a little longer. I'm heading back to Detroit soon, but if you got any more questions, feel free to grab me. And like I said, I think, yeah. Thank you. That's my, you can find all my stuff there. I don't do the Twitter. I don't do the Instagram, none of that stuff. So, look me up on GeoCities, though. Down and look at my terrible code. So that's kind of the reasons to use protobuf. Some of the reasons that you might not use it is if you have really big data sets. The Google protobuf page says if you're sending like more than a megabyte in a chunk, maybe think of something else. That said, I read in a forum recently that somebody was complaining about, we're not so happy with protobufs because we're throwing around 64 megabyte packets and it's just not holding up. It's like, well, it wasn't designed for that. And as you asked, it's a binary format. They're not interested in making this human readable or editable. This is something that you put in the pipe, it shrinks it down, sends it over the pipe, or maybe you're saving data, to a hard disk or whatever. But the idea is it's not meant to be something you can just open up a browser and say, oh, well, let's look at all the fields in this structure. That's not going to happen. So, and because of that, you can't do things like interleave other, like like XML, it's really easy to stuff some JavaScript or HTML or something like that in there. But this, you're not going to do that. All right. Okay. So yeah, thanks for coming to my talk. This is my first Pi Ohio talk, actually second time attending, so pretty excited to be here. I'm excited that I could wear the shirt somewhere and have people get it, and not instead of look at, like I'm making some kind of political statement or something. So I'm excited for that too. A little bit about me. I've been in the software biz for a long time now, mainly doing C, C++, mainly doing C, C++ development, but a lot of incidental Python. So I'm definitely not a Pythonista by any stretch. So any misstatements I make are out of ignorance, not malice. But so this thing that I'm going to talk about today, Google protobuf, is something that I've used it's just popped up time and time again as a good tool to fix problems that I've encountered. So let's get on with it. What are protocol buffers? They're designed by or developed by Google. It was developed as one of their, what they call them, 10% projects. They're extracurricular projects. So, but it's been widespread adopted throughout Google. They use it in, I don't want to say all of their projects, but many of them. It's an extensible language, platform neutral, efficient way to encode data. So, yeah.
Okay.
So, at its core, what it does is it takes various arbitrary data, makes it as small as possible, not using compression, but just using clever encoding. And as I said, it's widely used in Google. I think I read on their in the GitHub page that somebody did a search of their repo, and there's over 40,000 .proto files, which are kind of the source code of that. So it's open source and patent free. So that's all good. The three benefits that you get from protobuf that gets me coming back to it time and time again is the backward compatibility is easy to get. They designed it for that purpose, so they don't have to upgrade all. There's a simplicity there that you may not get with XML, at least not that I'm aware of. It's really in addition, so what attracted me to it for this talk is that it's, in addition to using it at large scale deployments all over the world, you can also use it for very limited bandwidth or limited RAM, limited storage, so forth. So like little devices. So that's what I'm going to show later. I've got some kind of antiquated little devices, but that's what I had, so that's what I went with. Did anybody go to Greg Svoboda's talk yesterday? No?
Yeah.
Okay. He showed off this little $5 system on a chip, the ESP 8622, or 8266, yeah. And it was, he threw an Arduino into the audience that here, you can have this. You don't need to use these anymore because that thing is pretty awesome. So I don't have those, so I have something maybe hopefully a little more familiar to people who aren't into like small computing devices. So, and I should add that all this, everything, the slides and my code and everything will be, it's on GitHub. So at the end there'll be a links page, and so you can pull all this to other servers at the same time to talk the same language. The encoding is very efficient, and the code to parse these buffers is automatically generated. So there's not a byte of handwritten code where you have to, oh, this is this kind of field. I need to convert that to an int or whatever. It's all built in. This was largely stolen from their protobuf GitHub as well. Basically, they made a comparison to XML. The XML is great for a lot of things. I use it a lot. It's very, very readable. It's very wordy, though. If you're doing something at scale, so either something at the scale of Google, where you have, I don't know how many, tens of thousands, hundreds of thousands, however many servers they have, they need something that scales. And when I don't want to see what their bandwidth bill is, but shaving 1 byte off of every packet they send to their server, I'm sure saves them, a lot of money. So compared to XML, it's 3 to 10 times smaller, 20 to 100 times faster for parsing. The data accessors are automatically generated, so